All right, welcome to section 4.7 on LHopitals Rule. We're going to jump right into this and just remind ourselves that this is our motivation. When we were dealing with the derivative of e to the x, in the middle of that proof, we ran into this limit. And we just stated that this was what the limit was. I think we maybe picked some numerical approximations by looking at numbers close to 0, plugging them in and saying, oh, look, from the left and the right, it looks like it's getting close to 1. Great, that's probably what the limit is. It's a hard limit to do analytically. And so what we're going to do is try and come up with a rule. Well, we're going to look at the rule that'll help us out. The key here is that when we look at this limit as h goes to 0 of e to the h minus 1 over h, if we start plugging things in, we get this indeterminate form. And indeterminate form limits are hard. That's essentially what we're going to deal with. We're going to look at these indeterminate form limits and see how we can sneak through them a little bit quicker. This is our rule. LHopitals Rule is not terribly difficult, so let me just read through it, and then we'll kind of talk about how it's going to work. So as long as f and g have derivatives that exist around this point A that we're going to be looking at, that x is going to be getting close to, and the denominator, notice whatever the g function is, that derivative can't be 0. It probably makes sense why. If it was, then we'd have something divided by 0, and that would screw us all up. So if both the limit of the top and the bottom are equal to 0, essentially, if when we try and do this limit, we get this indeterminate form, 0 over 0, then what we can do is just look at the derivative of the numerator and the derivative of the denominator separately. The confusing thing is that we don't use the derivative of the whole fraction. We're not doing quotient rule here. We're doing like the fake bad version of quotient rule that we maybe almost got tricked into using before. Derivative of the top over derivative of the bottom. So we're not looking at the derivative of the whole thing. We're just looking at the ratio of derivatives, which is kind of weird. And as long as this limit here actually exists, or if it diverges off to infinity or negative infinity, then that's what our original limit was. We can do this with limits at infinity, one-sided limits, anything weird. So we already said that this was 0 over 0, so it's a prime candidate for LHopitals Rule. So what we'll do is take a look at the limit as h goes to 0 of the derivative of the top, which is just going to be e to the h, over the derivative of the bottom, which is just 1. So we have e to the 0 over 1, which is 1 over 1. Sure enough, that limit that we were looking at in the proof of the exponential derivative is really 1 using LHopitals Rule. And that's all we've got. So anytime we see this 0 over 0, go ahead and differentiate the top and bottom and see what we can do. Here's a couple of examples. With something like this, we can go ahead and just check to make sure that when we plug things in, we actually do get 0 over 0. I'll let you check that, but we do here. So that means what we can do is look at the limit as x approaches 3 of 3x squared minus 14x plus 12 all over 1. So when we go ahead and plug 3 in here, we get 27. 14 times 3 is going to be 42. And then plus 12. So that ends up being, what's this? 27 plus 12 is 39 minus 42 is negative 3. So that's what that limit is. This trig one is kind of tricky. We've got x times cotangent of x. So what we'll do is rewrite cotangent as cosine over sine. That's a nice thing to notice. So now we've got 0 over sine of 0, which is 0. So let's use LHopitals Rule. We're going to take a look at the derivative of the top and the derivative of the bottom. On the top, you're going to have to use a product rule. I'm going to just skip through that because you guys can check it with the product rule. We'll say this is going to be the limit as x goes to 0. The product rule is going to be x times negative sine of x and 1 times cosine. So I'm going to say cosine x minus x sine x over the derivative of the bottom is going to be cosine x. And now when we plug in 0, we get cosine of 0, which is 1, minus 0 times sine of 0, which is 0, over cosine of 0, which is 1. So this is just 1. So these work out to be pretty easy as long as we keep our wits about us. Don't do the quotient rule on these. Just take a look at the derivative of the top and the derivative of the bottom. This is where things get a little bit tricky. We've got some other versions of indeterminate forms these are the two basic ones that we're going to look at. We already know how to deal with 0 over 0, and what this theorem says is that L'Hopital's rule holds if we have something like infinity over infinity. Notice it could be positive infinity over negative infinity, or negative infinity over positive infinity, or maybe both are positive or both are negative. Doesn't matter. We're all going to just call it infinity over infinity. And if we have that, we can just take a look at the ratio of derivatives and the limit of all that stuff. It's the exact same process. It's the exact same thing. So that I'm not worried about. What we do want to think about is these other indeterminate forms. They're going to be a little harder to deal with. That's going to be where the tricks are involved. So let's show off this infinity over infinity one. We'll see how easy it is, and then we'll move on. I might not even do both of these examples. With this one, let's just notice right off the bat that we could do this without L'Hopital's rule. We know how to deal with rational functions. We know that we're just looking at the ratio of first terms here because they have the biggest power. So we know that this thing is going to be 3. Now, that's what we're going to know. Let's just use L'Hopital's rule to check this. So if we put infinity in here, sure enough, we get infinity over infinity. So if we want to check it using L'Hopital's rule, we're going to look at the limit as x approaches infinity of 18x minus 4 over 6x. This one, again, would be infinity over infinity. So we'll do like another step of L'Hopital's rule. And we'll take a derivative again of the top and the bottom. And now we just have 18 over 6, which is 3. Just like we knew it was, because 9x squared over 3x squared is just 3. So everything works out pretty easily there. You'll notice here, this one ends up being infinity over infinity as well, because our tangent function and secant function both have asymptotes at pi over 2. Now you'll notice I didn't really care if the asymptotes are going up or down here. I'm not putting my signs on all this stuff, because it doesn't matter if it's positive infinity or negative infinity. As long as we have infinity over infinity, that's that indeterminate form. We'll take a look at the derivative. We're looking at the limit as x approaches pi over 2 on the left. The derivative of 1 plus tangent is just going to be secant squared of x. The derivative of secant of x is secant of x tangent of x. Notice that some of the secants can cancel out. So this is really a limit as x approaches pi over 2. Let me fix that. From the left of secant of x over tangent, which is really 1 over sine of x. Because secant is 1 over cosine, tangent is sine over cosine. So we could say this is cosecant, but I'll just write it as 1 over sine of x. And now we know that sine of x is 1 at pi over 2. So this limit is just 1. And that's what our original limit is as well. So these infinity over infinity indeterminate forms aren't any more difficult. So all we have to look at now, there we go, is some strategies for these other indeterminate forms. When we have two functions that are multiplied by each other to get this 0 times infinity, what we're going to try and do is get a quotient instead of a product, because we know that if we have a quotient, we'll either have 0 over 0 or infinity over infinity, and we can get some nice little L'Hopital's rule action going on there. So instead of multiplying, we just divide by a reciprocal. So if the thing that we put in the denominator, this f of x, if that was the one going to 0, then now we've got 1 over 0 in the denominator, which goes to infinity. And if this was the one that goes to infinity, then we have 1 over infinity, which goes to 0. Either way, most of the time, it's going to match up with what the thing on the top is. Doesn't matter which one you do. Doesn't matter if it's the first or the second one, but do whatever one you think is easier. Instead of multiplying, divide by a reciprocal. That's kind of a clever trick to get it set up into one of these forms, infinity over infinity or 0 over 0. So keep an eye for that. This one's a little harder when you have a difference of two infinities. That means you've got a function that has two different terms that are subtracted. You can try and factor this out, pull out a common factor to write this difference as a product of two things. Sometimes you can use a change of variables. This is a nice change of variables to look at here. And so then instead of looking at something with an x in it, just put 1 over t. Notice that when x goes to infinity, if we put infinity in this denominator, t goes to 0, but it stays positive. So your limit changes as well. So keep an eye out for that variable substitution. You might see that in 1 or 2 homework problems. And then lastly, we've got these exponential functions. 1 to infinity, 0 to 0, or infinity to 0. These types of exponentials are indeterminate because, again, notice that this isn't actually 1 to infinity. It's something that's approaching 1 raised to something that's approaching infinity. So the idea is, well, maybe the thing that's approaching 1 isn't approaching 1 quick enough, and so there's little slivers of things bigger than 1 or smaller than 1 that when we raise those exponents, maybe it has something to do with something. Who knows? So here we have a function f raised to g. Notice that all we really do is we write this as e to the natural log of f raised to the g. Normally, we'd say, oh, the e and the natural log cancel out. So these two things are really the same. But now we can take this exponent of g and bring it out front. And what we really have is e to the g natural log f. What we will do is focus on just this exponent. We'll call this capital L. And we'll notice that whatever this limit is, that helps us find our original limit pretty easily. Our original limit is just going to be e raised to that L, whatever we find, if that limit exists. So that's a nice little trick. We take that exponential and we use e to the natural log to simplify it so we can just focus on the exponent. The last thing I want to show you is this nice little growth rate intuition. This chart just helps us categorize how quickly functions grow up to infinity. You could think like a logarithm function that looks like this, and a linear function that looks like this, and an exponential function that looks like this. They all go up to infinity as x approaches infinity, but they do it at different speeds. This log is the slowest, the linear one is in between, and this one blows up to infinity pretty quickly. That's what this chart really compares. Our slow ones are logs, even with exponents of them, so log squared is pretty slow. Polynomial functions grow to infinity faster. If we increase the degree of our polynomials, they go faster, so x cubed goes to infinity faster than x squared. Exponentials go even faster, and bigger bases are faster than smaller bases, so 10 to the x goes faster than e to the x. And then this weird x to the x function is the fastest one of them all. What this does is it helps us look at limits like this one, e to the x plus 1 over the natural log of x minus 7. And I immediately know what's going on. Because I know as x goes to infinity, this exponential function here goes faster than my logarithm to infinity. So I'm going to end up with infinity on the top. Similarly, if I flip this upside down, and I have natural log of x minus 7 over e to the x, then I know that the thing that gets really big is on the bottom. So I've got something divided by infinity, so that limit's going to go to 0. I just know this based on my intuition because I'm pretty familiar with this chart. What we should do is use LHopitals Rule to check these, because this is going to be infinity over infinity on both of these. So we could take a look at the derivative of the top and the derivative of the bottom and make sure that these limits actually do equal infinity and 0. But using this little comparison of growth rates, we can at least build the intuition. This is everything we really need from LHopitals Rule. Jump into your homework, keep an eye out for those weird indeterminate forms where you can use some of the tricks that we've described in here. But that's really all you need. So go and get some practice on those homework problems.